Hello everyone, we are in our plasma class and in this class we will be starting plasma sheath which we already started in our previous class. So what we are doing, plasma in touch with the wall, and wall absorbs both electrons and ions, but due to higher mobility of electrons the wall potential adjusts itself to be negative with respect to the surrounding plasma. The repulsion of electrons by the negative wall results in formation of a positive space charge region called plasma sheath that shields the neutral plasma from the negative wall. The typical extension of the sheath is of the order of Debye length, and the sheath is planar and assumed to be collision free. The substantial distortion in the ion distribution due to wall losses requires Bohm criteria, a criteria that will be deriving to be satisfied for effective shielding. So, this much what we did in our previous class, and when we apply a potential difference between the cathode and the anode, it the bulk plasma mostly remains your field free. A small drop is there, this is the plasma drop, and most of the drop occurs in the sheath regions. The kind of variation of potential that I have shown in this diagram, this is just a representative one. There are lots of variation, this structure of this potential in the sheath region, so which we will be discussing in our tutorials. This is just a representative of the kind of potential distribution that may happen over there. Okay, so we start with this, and then let us try to understand the sheath region in this class. Okay, so for a formal mathematical framework, we define that the wall of the plasma container is at Z is equal to 0 here, and then the plasma sheath is the white region here, that is extending up to, as I told you, that of the order of Debye length. So, this lambda d we have written here, and then the bulk plasma starts. So, towards this the bulk plasma, and as you are seeing here that Z is equal to minus lambda d, where this sheath ends and then the plasma starts. So, this is a typical presentation of the sheath that we are trying to consider. So, we also assume that the plasma is non-magnetized here, contains singly charged ion in contact with an absorbing wall. Due to negative charge of the wall, most of the electrons are repelled. Now, the thermal electrons are therefore hardly distributed by the wall losses and can be assumed to be in Boltzmann equilibrium. So, this is for the electrons. But the distribution of ions are strongly distorted due to the wall losses, and ions are not in Boltzmann equilibrium. So, in this consideration, we will be assuming one approach for the electrons, and we will be assuming that the electrons, the thermal electrons are actually disturbed by the wall losses. These thermal electrons are not disturbed by the wall losses and can be assumed to be Boltzmann equilibrium, because they are anyway getting repelled, they are not getting absorbed by the wall. So, this term what is distributed should be actually disturbed by the wall, and so they are maintaining the Boltzmann equilibrium because they are not undergoing into losses, whereas the ions are strongly distorted by the wall loss, because you see that this is negative and they are getting attracted strongly by the wall. And in fact, actually, to maintain the charge neutrality, that is same number of electrons and ions are reaching the wall, to do that they need to provide an electric field, additional field, which will attract the ions so that they can compete with the faster electrons, and finally they meet that the net charge that is reaching the wall is same, because electrons will be moving anyway very fast over there, but ions are not being able to move. But if that non-equilibrium, I think that I mean that the electrons, if they reach more in number than the ions, then you can assume that it will be always some current will be passing through that, right? Because there will be net charge which is accumulating over there. But once the potential develops over there, that is negative potential, then they are retarding the electrons. So they tell that no more electrons are required over here, but come more ions, so that I can neutralize the net charge, that is electron number same as the ion numbers over here. And we'll show you at the end of this this exercise that they are really maintaining under certain conditions. And what I just told you, that it is the Bohm criteria. This is basically the criteria that is maintained actually when you want the sheath region to exist over there. Unless it is satisfied, the sheath actually doesn't exist. Okay. So for formation of the sheath, you require the criteria to be maintained. So that is the Bohm criteria, and it appears as a natural consequence of the kind of phenomena that you are seeing here, and we will just derive that from a very simple consideration. And don't worry about the mathematics; they are pretty simple, and you can do that. Okay. Now, as I told you that we assume that the wall stays at z equal to 0 and quasi-neutral plasma start from z equal to minus lambda d. So we define several parameters at the boundary of the quasi-neutral plasma at any point P within the sheath, okay, inside the sheath. So these are the parameters we define, that electron density at the boundary of quasi-neutral plasma. So here actually, so that is N0. Ion density is also N0, because you know this charge neutrality has to be maintained. And as I told you that we are considering only singly ionized charge over here, then ion velocity is Vz0 at this boundary of the quasi-neutral plasma. And then z coordinate is minus lambda d, as I have shown you over here. Then plasma potential is 0. We are assuming that. Okay. So you know that potential is basically, it is the difference in potential that matters all the time. So we can set it to 0, and all our purpose is to extract the physical behavior, nature of the plasma sheath, how it may behave, so all those things. So that's why we are making some approximation, like we are saying that it is a singly ionized plasma, and we are assuming that the sheath starts at minus lambda d. So all these are realistic. All these are realistic, and doing this, these are not breaking the physics. So this is only some assumptions which are very in agreement with the kind of physics that may be evolved here, and we will come to know about the kind of behavior that is expected in such region. Okay. And then at the point P, that point P is within the sheath, and there what we are assuming, that electron density is Ne, ion density is Ni. Now we are not assuming they are the same. Okay. And then ion velocity is here we have said that Vz, and z coordinate is minus z, any z is over there, and the plasma potential is U. Okay. Not it is 0, because this is a non-neutral region. So we are assuming like this. Okay. So we now refresh once more that we are assuming a configuration where this is the wall that is staying starting at z equal to 0, and adjacent to wall there is a sheath which extends up to z equal to minus lambda d. It may be of the order of lambda d, exactly not, but we are assuming that it is that minus lambda d. and beyond that the bulk plasma starts. So this is the boundary of the quasi-neutral plasma. Here the electron density is n0, ion density is same as electron density, that is n0. Ion velocity is Vz0 here, and the z coordinate is minus lambda d, and plasma potential we are assuming as 0. Okay, and this is the sheath region. Here any arbitrary point we are taking as P, and basically this is the region where we are interested in, and this is so thin usually that experimentally it is very difficult to do experiment, and we mostly go for modeling, and different assumptions result in different kinds of picture. Mostly they agree with each other except some finer details. So this is the kind of parameters that we are interested in: the electron density distribution, ion density distribution, ion velocity, and then Z, these are the potential, plasma potential. Okay, so we start with this configuration and with this parameter listing, and we enter into the sheath equations, and I am sure that you will be appreciating these equations. And this is one method which is called non-dimensional techniques. So we will make this dimensionless, this analysis completely dimensionless, and that will help us in scaling up. So it is in terms of dimensionless parameters, so you can it becomes applicable to a broader range of systems. Okay, so how we defined? So here you are seeing that half mi Vz square. What is that? That is the kinetic energy, and we are scaling in terms of kTe. So this is basically ratio of kinetic energy, and this is this kTe, this is the thermal energy. So this ratio we define as y. So this is a dimensionless parameter because this is energy divided by energy. Similarly, for potential energy, EU, again we scale it in terms of kTe. So this becomes dimensionless parameter. Okay, chi equal to minus EU by kTe. Then Ne, the number density, we again make it a dimensionless and divide by the N0, the bulk number density, bulk plasma number density. Then this Ni, again your ion density, this is again scaled in terms of bulk, your plasma density N0. So this is Ni by N0. Now comes the distance. So this distance is Z in this direction, and we have our common friend this lambda d. So this is dy length, we divide it by that and we get the dimensionless distance. So this is dimensionless distance, this is dimensionless number density, this is dimensionless electron density, this is for ions and this is for electrons, both are number densities. This is dimensionless potential and this is dimensionless kinetic energy. Okay, so now we will be writing all the equations in terms of dimensionless parameters. Now we will be asking, why are you trying to do so? So one thing is that I told you that these are, when you define something in terms of dimensionless parameters, then scaling up is very easy, and when you switch from one system to another system, you can interpret your results in a much better way. The other thing is that we are trying to arrive the condition for existence of plasma sheath, whether they will be always existing or there will be some condition which needs to be met for the sheath to exist. So these are the things. Now, as we told that electrons not undergoing losses because the field that has been generated over there, that itself is not allowing that to get lost over there on the wall. Okay, so ions are on the other hand, they are they are dragged towards the wall by additional electric field generated due to the negative potential of the wall, and in that case what we will do, that current continuity will be maintained, that whatever ions is crossing this region, they will be reaching the other region as well. So that is the current continuity equation, and we will be using that for the ions. But for the electrons, we can very well use the Boltzmann distribution. So what is that? Ne equal to N0 exponential of minus EU by KT. So what is the U? U is the potential in the sheath region. okay, here. So depending on the potential, the retardation it will feel and their distribution will be adjusted. So this is the potential at that, in the seed region minus u is varying and is a parameter which is varying with the z, and what we are getting, this is the number density Ne equal to N0 exponential minus U by Kt as per the Boltzmann distribution. So we now want to write it in terms of dimensionless parameters. So we divide both sides by N0, and this side becomes Ne, the dimensionless electron density. This side N0 cancels, and what we get, Eu by Kt. Again, you know that this already defined as a dimensionless parameter. So anyway, exponent becomes dimensionless. This is the property of the exponents. So this is minus chi. So as we have defined this chi over here. So we now get the electron density distribution in terms of dimensionless parameter as this, Ne equal to exponential of minus chi. Now for the ion current density, you know that we have already told that the current continuity should be maintained. So divergence of Ji equal to 0, and that is giving you del Ji by del Z equal to 0. In this Z direction the ions are moving. So what you are getting, Z is equal to NeV, E will be cancelling. So N0 Vz0, that is at the plasma edge, that will be equal to Ni Vz at some arbitrary point P. Now again we come to our dimensionless practice. So here what we do actually, this Vz0 is equal to Mi Vz square by 2 kte. Okay. So what we are doing, this Vz whatever is there, this Vz we can write as square root of Vz square, and Ni we can divide by N0, so this becomes small Ni, and you are seeing that on both sides, this as well as this, we are multiplying this term root over Mi by 2 kte. This is there, then this also is there, and this is Vz square root of Vz square we have made, and this we have made square root of Vz0 square. So this equality now maintains, and because we have divided Ni by N0, so this Ni appears only on one side, and what we get in terms of dimensionless parameter, you see that the way we have defined over here. So it is now becoming Ni, this is y, you see the definition. So y to the power half is equal to y0 to the power half. What is y0? This parameter, dimensionless energy, kinetic energy, and that is, this y0 is representing at the plasma edge, and this y is representing the kinetic energy at any point within the sheath. So this is the equation what we get from the current continuity equation, and this in fact gives you the expression for distribution of ions, and this one is distribution of the electrons which we obtained from the Maxwell distribution, and this one we obtained from the current continuity. So we now get the electron density distribution as well as ion density distribution within the plasma sheath. Okay. Now there is something, ion energy conservation. So what is happening here, the potential we are assuming that 0 in the this plasma zone. So what is there, the kinetic energy is half m v0 square, and you are saying that the potential energy is 0. But here what it is getting? It is getting the potential energy EU and the kinetic energy half m v0 square. So both of them will be added. So if I want to write the kinetic energy only of the ions, then this goes on the right side, and then what you get actually the conservation from the conservation equation, conservation of energy, that Mi Vz square equal to Mi Vz square minus EU. Then what you do, you divide both sides by KTE, because this half is there. So you are getting KTE over here, KTE over here, and this KTE over here. Now as per our dimensionless parameter definition, what we are getting, this is nothing but y, this is nothing but y0, and this one is nothing but chi, the potential energy. So, what we are getting? Y equal to y0 plus chi. So, we now have three very important equations. One is electron density distribution, one is ion density distribution, and one is energy conservation equation. Now, we will use these three basic equations in the remaining of the derivations to reach the condition for formation of this plasma sheath. Okay. So, we start with this, and you remember these three equations, and we have explained how they have how we have arrived to these equations. Okay. So, now we go to the next slide, where we will be using this equation and we will try to find out some useful information. So, here we come. So, y equal to y0 plus chi. This is just the last equation that you started with. Okay, this is one. Now, when this is a thing, then Ni is what? As per the definition, Ni equal to Ni by N0. Okay, and here what we got? Ni equal to y0 by y to the power half from this one. Ni equal to the distribution of ions, that is y0 by y to the power half, or y by y0 to the power minus half. You remember that. Now, Ni equal to y0 by y to the power half, as we have told. So, y by y0 to the power minus half. Now, y by y0 is what? 1 plus chi by y0. So, this 1 plus chi by y0 to the power minus half you are getting over here. Now, as usual in all problems of this plasma related thing, Poisson equation come as a rescuer to us. So, here also it is no difference. This is the Poisson's equations, del square u is equal to rho by epsilon. Okay. So, this is the z direction equation. So, what we are getting, d to u dz2 equal to Ni minus Ne by epsilon, and this is giving you the dimensionless expression for this Poisson equation. We are dividing this by kT, and you know that then you are getting that Eu by kT. So, this one actually you are getting from there. Then this side you are getting Ni by N0 and Ne by N0. Okay. This one, this Ni, this is divided by N0, and this is Ne divided by N0. So, this is Ni minus Ne. So, this is dimension equal to rho by epsilon 0. So, this N I and Ne, whatever you are getting, you are dividing by N0, so that you can get Ni, and so that here you can get Ne, and Eu by kT is equal to, what is that? That is equal to chi. And one thing you have probably missed over here is that this Z is now converted to xi. Okay. And what is Z and xi relationship? So, that was xi is equal to Z by lambda d. And what is lambda d? Lambda d is equal to epsilon kT by n square. Okay. So, that is the your Debye length. Yeah. So, if you use that, then this chi, if you write these equations in terms of chi, then this kT appears over here in this Z, and that kT goes up, and you are getting these expressions in terms of this this dimensional parameter chi, and here you can get this Ni by N0 and Ne by N0, and that N0, what is coming through that this thing, what you call Debye length lambda d, that is getting absorbed over here. So, if you put the expression for xi including the form of lambda d, then you get this expression from this Poisson's equation. So d2 chi by dt2 equal to ni minus ne. So this is another important equation. What you got in terms of xi, that is z by lambda d, the lambda d expression we have now put over there. So root over epsilon kt by n square. Now what we come over here, that d2 chi by t xi 2 is equal to ni minus ne. So this is the one. Now this one ni minus ne, we put the expression for ni. What is that? This is 1 plus chi by y naught to the power minus of, just what we have got on the top. And ne, as we got in our previous equation, that it is exponential of minus chi. So we just put over here exponential of minus chi, and then for mathematical derivation we multiply both sides by d chi by d psi. So if we do that, then you see that every term is multiplied by d chi by d psi, and then what we are getting here, we can get it at d psi of d chi by d psi square into half. Okay, that we can get. You can just simply connect these two, and then this one you are seeing that we can write this as a derivative of this quantity, and this one you know that it is exponential, so we can always write it like this. So the right hand side is written as dt chi of some quantity, and left side is also written as dt xi of this quantity. So both sides are derivative with respect to xi, and here we do have in the argument d chi by d psi square, and here this is the complete expression what we are having. So now you can understand, then the argument whatever there in this side and this side, they will be equal with a difference of constant. So there will be some constant, but this term what is there in the within the bracket will be equal to this term plus some constant. Okay, this is very obvious. So we write that some constant C1, and what we did, you see, you know the term, this factor half over here, and this half is getting, this 2 is getting multiplied on the right side. So we get 4 over here and 2 over here. So and the 2, that factor is absorbed in this constant C1, so we are not bothered about that. So finally what we get, d chi by d psi 2 is equal to this plus C1. Now when psi tends to infinite, okay, what is psi? Psi, then you know the potential, this is the chi actually, okay, this is the psi. So when your psi is becoming very large, then you are entering into the plasma, okay, and that point you know that the potential is not varying within the plasma, so you are getting the potential is 0, as well as derivative of this you know chi, that is also 0. So if that is the case, then C1 what you are getting as just you know chi is 0, so you are getting that C1 is equal to 4 minus 4y0, because this is on the same side, and minus 2, this one is giving minus 2. You put that thing over here and you get this expression. What you are getting? That d chi by d psi square is equal to this one plus this one. Now you can just expand this one, because you know this chi is the potential energy and y0 is the kinetic energy, okay, and you know that in plasma the basic criteria to form is that y0 should be much greater than chi. So that is the basic criteria. If that is the case, then what we can do actually, we can expand it up to certain term and then leave the remaining terms, because this is a small quantity. So we expanded it over here, kept up to the first and second term, and then we have put this minus 1 over here. Similarly, this exponential term, you know, chi is small because this kT is the thermal energy and U by kT is small. So we again expanded this one, and what we are getting, that this when you put over here, then you simplify and you can easily see that this is 1 minus 1 by twice y0 chi square plus of the order of some term chi cube, and chi is small, so we can neglect that thing. So what we get, this one square is equal to 1 minus 1 by twice a0 and then chi square. You just note down the form. Left side is square, right side there is another square. Left side is square means it should be definitely positive, and this term is positive, so this term must be positive. You got the point. This term is positive because it is square. This chi square is a square quantity, so it is positive. Since left side is positive, right side also should be positive, and this one is positive. So this term 1 minus 1 by twice a 0 must be greater than 0. So this is the condition, and y0 must be greater than half for the C2 form. Okay. So this criteria y0 is root over, if you put the expression over there, then you get that Vz0 must be greater than square root of kt by mi. So this velocity kt by mi is called the Bohm velocity. Okay. So this Vz0 must be greater than Bohm velocity. We will be explaining a little more this in the next class, and I stop here. So see you in the next class. Thank you.